Hello, everyone, and thank you for the invitation to present at Sharif. It's a great honor to be here virtually, and I'm going to present some recent work that I did with my PhD student Rohan, who's at Michigan, and colleague Anupam at Carnegie Mellon University. And again, please feel free to ask questions during the talk. I think that'll make the session more interactive, especially because it's virtual. I can't see your reactions or understanding or lack of understanding on your face. And I mean, it's not supposed to be very complicated, so I'm happy to address questions at any level. So in traditional optimization, we have mathematical models with various input parameters. However, all these input parameters are assumed to be known precisely, or they are assumed to be deterministic. So if you think of a sensor placement application, we may need to know the exact area of coverage of every sensor before we can solve such an optimization model. However, in practice, many of these input parameters are random and we don't know their precise outcome upfront. We may have some probability distribution of the possible outcomes. So, for example, we may know that the sensor may end up covering either this red region or the blue region or the green region in the picture in the bottom. But we may not know which exactly it's going to cover before we take the corresponding action. So stochastic optimization is an area that deals with these kinds of optimization models. We have problems with certain input parameters that are modeled as random variables. And we want to make our decisions so that we satisfy some constraints and we optimize an expected objective. So that's going to be the focus of this talk. A key thing in the stochastic setting is that describing a solution is somewhat more complicated. So here, a solution is really a sequential decision process where at every step, we get to perform some action or take some decisions, following which we will observe some random outcome associated with that action. So in sensor placement, you can imagine that at each step, we place a sensor at some location. And after that, we will get to know what exact area did that sensor cover. But before we perform the action, all we know is a probability distribution. So such a solution is also called a policy, and it's easy to represent it by means of a decision tree where every node, like that one, corresponds to some action that you take at that point in the solution, and the branches correspond to the random outcome that you observe. So maybe you observe a positive or a negative outcome, and that sort of updates the state of the solution or policy. And another way to represent these solutions is by means of a stochastic dynamic program. But no matter how you represent these solutions, they typically require space that is exponential in the number of input parameters. So it's not the ideal way to solve these kinds of problems because they don't scale very well with the size of the instance. So let me motivate our setting with the sensor placement application. So what we want to do is there is some target region, which is the red rectangle in this picture, and we want to activate or place the minimum number of sensors so that we manage to cover this region entirely. But upfront, we don't know the exact coverage of every sensor. We do know its probability distribution. So what can a solution look like in this application? We can first place some sensor. Let's say we place sensor 1. And once we place it, we can observe what exactly it covers. This might require some amount of time to wait because it requires time to sort of capture or cover the region around it. So we wait for some period of time and see, okay, sensor 1 covered this particular blue blob. After we have observed what sensor 1 covers, we can decide to place the next sensor, which is sensor 2 down here. And again, we observe what sensor 2 covers. That's this bigger region. And then we decide to place the next sensor, number 3, observe what that covers, place the next one, 4, observe what that covers. And at this point, we can see that collectively, the 4 sensors that we've placed have covered our target region entirely. So that's a good enough reason to stop. And on this particular decision path, we have spent 4 sensors. So the objective is going to be minimize the expected number of sensors that we place before we end up covering the entire region. And of course, different decision paths, the stuff that would be branching out of this particular path, they might behave differently. We might have decided to place a different set of sensors along those decision paths. So as you can observe, this solution is adaptive because it makes use of incremental information that it observes after placing every sensor. And because it makes use of all the information available at any point in time, it has the potential to have a low objective value or a low cost. But on the other hand, we also need to wait to observe the status of every sensor. We don't know instantly what is the region that a sensor covers. So once you place a sensor, you may have to wait for a few hours before you figure out exactly what was covered. And for that reason, the time taken to implement such a solution is going to be high, because every time you place a sensor, you're having to wait a few hours to see the result or the area that it covered. So a different kind of solution is what is called a non-adaptive solution. Just says, I'm not going to wait for every sensor sequentially. I'm going to figure out some list of sensors, for example, sensors 1 up to 6, and I'm just going to activate all of them simultaneously. So the good thing about this solution is it's very fast to implement, because we can just go and set up all these sensors and then wait simultaneously. So we don't have to do the sequential decision process anymore. But the bad thing is, because you had to pre-commit to the set of sensors that you activate, it's likely to be more expensive in terms of the objective value. So what we've seen is, for this sensor placement application, there are 2 kinds of solutions that have these kind of extremal behavior in terms of the cost, which is the objective value, and the implementation time. So an adaptive solution tends to have lower cost but higher time to implement. On the other hand, the non-adaptive solution has higher objective value, but it requires less time to implement. So a natural question, and that's going to be the focus of this talk, is whether we can find a smooth trade-off between these 2 extremes. So we would like to identify other types of solutions that get somewhat better time than the adaptive solution, but they get much better cost than the non-adaptive solution. So stuff in this middle region that I've drawn over here. And we will quantify this by rounds of adaptivity, where in every round, we are taking some decisions in parallel. So we don't have to wait for the random outcomes to realize in a sequential manner. So if we have only a small number of rounds, then the implementation time will be smaller. Of course, having a single round would correspond to a non-adaptive solution, and having an unbounded number of rounds would correspond to an adaptive solution. So we want to sort of trade off between these 2 extremes. Here's a second application to motivate our setting, and this is in medical diagnosis. So we have a bunch of possible diseases that a patient can have, and we have a priori probabilities of each of these diseases occurring in the patient. And our goal, let's say as a physician, is to perform diagnostic tests so that we identify the disease using the minimum expected cost of testing. So notice that in this setting, the outcomes for the tests are going to be random because we don't know the eventual disease. That's our goal. If you knew the actual disease underlying the patient, of course, all the test outcomes would be deterministic, but that's precisely the point of this problem. We want to determine the unknown disease. So what would a solution look like? Again, we could start by performing test one. So let's say test one has positive outcomes on the diseases shown to the left of this blue line and negative outcome on the diseases shown to the right. And after performing test one, let's say we observed a positive outcome. What that means is we can eliminate all the diseases that would show up as a negative result on test one. And I've highlighted the eliminated diseases in the picture on the left. So the blue region shows the diseases that can be ruled out based on the observation that we just had. Because test one was positive, we can rule out all these diseases on the right side. Now that we have a smaller set of candidate diseases, we could choose the second test appropriately. And let's say we choose this test number 2. We observe an outcome of negative, and again, that eliminates some further diseases. And then we decide to perform test number 3. Test 3 again eliminates some diseases. We still have 3 candidate diseases. We perform test number 4. That eliminates 2 more. And at this point, we have a single remaining disease that has not been eliminated. So that must be the underlying disease. Right? So that's the reason we can stop, and we have diagnosed this particular red disease. So again, notice that the way I describe the solution, it's adaptive because it's making use of all the information available at any point in the solution. But because it's adaptive, it is also slow to implement because we may need to wait several hours for every test result to show up. If we want to diagnose the disease really fast, everyone can guess what's the right thing to do. Just perform all the tests, right? Just perform all the tests in parallel and collect their results at the end of the testing, which happens quickly because it's a single round. And then you'll be able to figure out what is the underlying disease. So clearly, this is a fast solution, but again, the cost for testing would be very high. So we have exactly the same question here. We have 2 types of solutions, adaptive and non-adaptive. They have different behavior in terms of the objective value and the implementation time. And we would like to identify other solutions that trade off between these 2 extremes. I'll stop here for questions on the motivation of these applications. Okay, if not, let's move on. So it turns out that both of these applications are special cases of the model that we'll consider, which is called stochastic submodular curve. So before I introduce the stochastic model, I want to explain the more basic deterministic submodular curve problem, which has been studied since the 80s. So here we have a submodular set function. So just to recap, what is a submodular function? It's a set function defined on a ground set of elements. So the set of elements is U. So we have a function value associated with every subset of U. And for the function to be submodular, it needs to satisfy these conditions shown in the blue box. For any 2 subsets A and B, if you add the function value at A and B, that should be at least as large as the function value on their union plus the intersection. And there are other equivalent characterizations of submodularity. This is one of them. And we are also going to assume that the function is monotone, which means if you take a larger subset, you have a larger function value. So these functions appear in many, many applications, and we'll see that they do capture the two applications we saw right now. And we will also assume by scaling the function that it only takes integer values, and we'll use capital Q to denote the maximal function value. So the maximal function value is the function value on the entire set of elements, so f of u. So that value will be denoted Q, and that will play an important role in our quantitative bounds. So in the submodular cover problem, we also have costs associated with every element. If we select an element E into our solution, we have to pay a cost of CE. And the goal is to select a subset of elements, S, that has minimum total cost, subject to the constraint that the function value on the chosen subset should be equal to Q. In other words, the submodular function should be covered. So covering a function means we pick a subset so that the function value is equal to Q, which is the maximum value of the function. Okay, so again, yeah, feel free to stop me if something is not clear in the formulation or the definitions. All right, so this is the, yeah. So there's a question, what distinguishes this model from RL? So can you expand RL? I see, reinforcement learning. So I think, yeah, so some aspects might be similar, but we have a particular setting where we have sort of, yeah, the setting in terms of adaptivity and observing information sequentially, that is very similar to the setting in reinforcement learning. But we have a more restrictive setting in terms of the objective being a minimum cost objective and the constraint being given by a submodular function that you can think of as a sort of a special setting within this general area. So the results we'll talk about will be focused on this particular setting of submodular cover and not general reinforcement learning. But the fact that you have adaptive solutions and sort of you sequentially observe outcomes, that is something that is similar in both the settings. Does that answer your question? Great. All right. So let's look at an example of a deterministic submodular cover problem just to get a sense of it. And we can indeed capture the deterministic version of sensor placement. And this is also called the set cover problem. For those of you who are familiar with combinatorial optimization, so here every element or a sensor covers some deterministic area, R sub E. In this example, it's this yellow rectangle. And there is again a target region that we want to cover in entirety. And the function that we will associate for any subset of sensors or subset of elements is the combined area if you include all of those sensors. So it's like we take the union of all the regions and take the area of that union. So in this picture, if you take the three elements E, G, and H, then the union of these three yellow rectangles will give you the function value of those three elements. And one can show that this is a monotone and submodular function, so it does fit in the framework that I just talked about. And the goal is to pick the minimum number of elements that will fully cover the target or that will achieve a function value which is equal to its maximum value. So the costs are all 1, and we just want to select some subset that will cover this entire region. So so we can see that this is a special case of submodular cover. So let's move on to the stochastic setting. So as we saw in the deterministic problem, we are still going to have a submodular function f that's defined on a ground set of elements. And again, remember that we assume that the value that the function takes are integers and q is the maximum value of the function. But in the stochastic setting, we have a bunch of stochastic items that are these blue points in the picture, where it costs some CI to probe any item I. So probing an item means you can observe the outcome that item realizes to. So every item is going to realize to a random element according to some distribution di. So we know the distribution of every item. So maybe this particular item over here will realize uniformly to one of these three elements that it points to. So with probability 1/3, it'll realize to this element here. With probability 1/3, it realizes to this one. And with the remaining probability of 1/3, it realizes to this third element. So we would know this probability distribution for every item, but we don't know the exact realization. So as an algorithm or a policy, we can select an item. And after we select the item, we will observe what element it realizes to. And after that, we can make our subsequent decisions. And again, we can choose to be adaptive and make sort of clever decisions, or we can choose to be non-adaptive and make a whole bunch of decisions upfront. So the key difference going from the deterministic to the stochastic setting is that we now have to select among these items where every item has a cost to select or probe, and we will only see the realized value after we probe that particular item. The goal is again the same. We want to cover the function f completely. So we want to make sure that if we have probed the items in S, then the function value on those realizations should be equal to the maximal value, which means we cover the function entirely. And because the outcomes xi for the different items I are random, this is going to be a random process. And so we want to minimize our expected cost. So an important issue that shows up is whether these item distributions are independent or correlated across different items. And we'll see that our results hold in both settings, but they will have different bounds depending on whether the distribution is independent across items or it could be correlated. So let's revisit the sensor placement application again and define it a little more formally. So now the sensors will correspond to items in the stochastic set cover problem. And the region covered by the sensor is going to be the realization. So for example, xi might realize to the square with probability 0.4, or it may realize to this rectangle with probability 0.3, or this other rectangle with probability 0.3. So we know that that's the expected behavior of a sensor upfront, but we will not know exactly what it covers before we place the sensor and observe what happens. And every sensor is going to behave independently of the others. So the probability distributions across sensors are going to be independent. The function f is the coverage function that we just saw in the previous slide. So that is a monotone and submodular function. And our goal is to minimize the expected number of items or the expected number of sensors that we place before we can cover this target completely. And covering the target is the same thing as covering this submodular function. Are there any questions on the model or how it applies to sensor placement? Okay, great. So this is an example where we have independent items. Let's now revisit the medical diagnosis application and formalize that again as a special case of stochastic submodular cover. So we now have some number of diseases. So let's say there are S diseases, where every disease has some probability of occurrence. The items in the submodular cover problem are going to be the diagnostic tests. So remember that every test is going to display a positive result on some subset of diseases, like that one, and a negative result on the other subset of diseases. So we introduce elements that correspond to test outcomes. So we'll have an element I plus, which means the result of test I was positive. We'll also have an element I minus, which means the result of test I was negative. So those are going to be the elements that will be associated with the submodular function. And to define the submodular function, we also need subsets for every element. For example, for element I plus, we have a subset which is all the diseases that will get eliminated if test I was positive, right? And in this example, it'll be these three diseases. Because if we know that test I is positive, we can eliminate them. And similarly, for I minus, we will have a subset covering these four diseases, because if test I is negative, we can eliminate those four diseases. So the submodular function is again going to be a coverage function. If we take any subset of elements, we just take the union of all the subsets, and we take the number of diseases in that union. So in other words, the submodular function captures the number of diseases that have been eliminated based on the test outcomes we have seen. So clearly, to identify a disease uniquely, we want to eliminate all but one disease. So we have to eliminate S minus one diseases. So the function value, the maximal function value will be S minus one, and that's going to be our target. So the goal would be to select these items or perform tests so that we eliminate all but one disease. And we've just seen that this can be viewed as an instance of submodular cover where you have random items because the test outcomes are going to be random. An important point here is that the distribution of different items are now correlated. So we can no longer say that the outcome of test 1 and outcome of test 2 are going to be independent because they are both correlated completely, in fact, by the realized disease. So we do have random test outcomes, but there are correlations across items. So this medical diagnosis problem can be formulated again as a special case of stochastic submodular cover, but with correlated distributions. So I mentioned that we are interested in solutions that can be implemented fast. So we formalize this by means of rounds, where in every round, we are going to probe or select some items in parallel. So we don't have to wait separately for the realizations of each of these items. So in an R round solution, we are going to have just R parallel rounds or parallel batches. So in the first round, we are going to select some set of items and probe them in parallel and observe all their realizations. And based on those realizations, we will identify a second subset of items to probe. That's what we will do in round number 2. Based on those observations, we'll go to round number 3 and so on. And we can iterate in this fashion only R many times, where R is sort of limiting the number of rounds. So what we need is to ensure feasibility. if we look at any decision path, that will tell us that we probe these items in round one, those items in round two, those items in round three, and so on. So if we take all the items that we probe along any decision path, then the function must be covered on those realized items. So that's what we require. And we can see that if we have no limit on the number of rounds, or in other words, the number of rounds is equal to the number of items, then you can be fully adaptive, because you can just take one item, wait for its realization, take the second item, wait for its realization, and so on. And the other extreme is if you have just a single round. If you are only allowed to probe items in round one, then that corresponds to a non-adaptive solution. So what we are interested in is to identify solutions that have a small number of rounds, but where the objective value is still comparable to the fully adaptive solution that has the best objective. So that's going to be the goal in our work. So just to formalize this a little bit more, we have the concept of an R-round adaptivity gap, which measures the ratio of the best R round solution. So an R round solution is limited to take only R adaptive batches. And we compare the cost of this kind of a solution to the best fully adaptive solution. So the fully adaptive solution can adapt or change its decision after every item. So that will obviously achieve the best objective. But we want to see how well can a limited round algorithm do. So notice that this question is just structural. It does not talk about an efficient algorithm to achieve such a solution. So we're just talking about two different solution concepts. One is an R round solution, where you're limited in the number of adaptive rounds, and the other is a regular fully adaptive solution. So this is one thing that we are interested in. But more importantly, we are also interested in coming up with efficient algorithms. So when we talk about an approximation ratio in this setting, what we mean is we mean an efficient or a polynomial time algorithm that comes up with a solution that only uses R adaptive rounds, but still its objective value is comparable to the fully adaptive solution. So we want to have the best of both worlds. So in the numerator here, the objective value of the algorithm needs to be something that you can find in polynomial time. But in the denominator, when you talk about a fully adaptive solution, there is we don't know how to identify these solutions in polynomial time. In fact, in many cases, we don't even know how to describe them using polynomial space, because these are stochastic dynamic programs with an exponential state space. So that's what we want to compare to. So one final thing in the background before we go to our results. So far, we have defined rounds in a set-based manner, where we take a static subset of items to probe in every round. And that is indeed the formulation which is most useful in practice. But in designing algorithms, it'll be more convenient to work with a slightly different model of adaptive rounds, where we have in every round an ordered list of items that we are going to probe sequentially until some stopping rule. So notice that within each round, we are still being sequential. But the good thing about this permutation round model is that we can cover the function with probability 1. So when we think of the original set-based round model, it's easy to come up with examples where to get any reasonable bound, you have to allow the function to remain uncovered with some failure probability beta. Because if you imagine that there's just a single round, then you fix your decisions up front, but there is always going to be some positive probability that your function will not be covered. And there's nothing you can do as a recourse action after that. So, so you will need to make sure that you'll need to allow the function to be uncovered or remain not fully covered with some probability. But when we go to permutation rounds, we can ensure that the function is always going to be covered with probability 1. And the permutation rounds will be easier to work with in designing algorithms. At the same time, we can transfer any algorithm that we design in the permutation model to an algorithm in the more practical set-based model. So if we allow for some failure probability beta, then we will have some increase in the approximation bound that depends on the failure probability, but it's sort of a smooth trade-off again. So if you achieve an alpha approximation using permutation rounds, then for any failure probability beta, you can achieve an alpha divided by beta approximation using set-based rounds. So based on this sort of transfer theorem, it suffices to focus on permutation rounds, and that's what we do in the paper. And that's also what has been done in prior work on this topic. Okay, I'll stop here for a minute in case there are any questions on the setup. Very good. So let's move on. So our main results are for the case of independent items, we show that we can get an R-round algorithm that has approximation ratio and adaptivity gap at most q to the 1 over r times log q. So as the number of rounds increases, imagine setting r as 1, 2, 3, and increasing it, you can see that the approximation ratio gets better as a function of q to the 1 over r. And it was known previously that the adaptivity gap has to be at least q to the 1 over r divided by some polynomial in r. So at least when r is a small constant like 4 or 5, which is most useful in practice, the upper bound that we prove is almost matching with the lower bound that was already known up to this extra factor of log q. When we consider the setting of correlated items, we again obtain an R-round algorithm that has approximation ratio s to the 1 over r times some logarithmic terms, where s is the support size of the joint distribution. So remember that in the correlated case, we will have a joint distribution that says what is the probability that some joint outcome on each of those items can instantiate. And the performance guarantee ends up depending on the support size of this joint distribution, and it can indeed be bad in many cases. So when you have a joint distribution over m items, the size of the support can even be exponential in m. So we also get a better approximation ratio using slightly more number of rounds. So if we use 2 times r rounds, we can get a slightly better bound. It eliminates one factor of r. But more importantly, we can also complement this upper bound by showing that there are instances where any r-round algorithm must suffer this kind of dependence on the support size. So the adaptivity gap has to be at least s to the 1 over r divided by some logarithmic factors. And this lower bound holds even when the function is just a linear or additive function and the target value is 1. So that's really the simplest possible submodular function. So the fact that you have a dependence on the support size is inherent when you deal with correlated items. And again, our upper and lower bounds are nearly matching up to a logarithmic term. Okay, so what was known previously for this setting? So going back to the deterministic submodular cover problem, a natural log of Q approximation was known due to Wolsey, and this is a setting that generalizes set cover. And for that reason, we cannot achieve any better approximation ratio, assuming that P does not equal NP. For the stochastic submodular cover problem, when you have independent items, a log Q approximation was known using a fully adaptive algorithm. And previous to our work, there was a very nice paper by Agarwal, Asadi, and Khanna that got an all-round adaptivity gap that was of this form. So I won't read out all the terms, but I'll just mention that we improve their bound by eliminating dependence on the cost of items and some extra factors of R. So we get a better result by roughly 2 logarithmic factors. And for the special case of the stochastic set cover problem, and even when the number of rounds is just 1, uh, there was a paper by Gomans and Wondrak that investigated this, and where they showed that the adaptivity gap using just 1 round lies between D and D square, where D is the number of objects that you want to cover in set cover. So it's some parameter specific to that problem. So the adaptivity gap had this quadratic gap between D and D square. And as a consequence of our result, we can tighten the upper bound to D times log D. So we now know that the adaptivity gap for this problem lies between D and D times log D. So in terms of the stochastic submodular cover, when you have correlated items, the fully adaptive case, again, was investigated earlier in this paper of Grammel and others, where there was a logarithmic approximation known. And this was also generalized to a broader setting by this follow-up paper. And there's also a different way in which people have modeled correlations in the stochastic submodular cover problem, which is the framework of adaptive submodularity. So this is a framework that captures the independent setting, but doesn't quite capture the correlated case that we consider. And in this setting, there is an algorithm that achieves a logarithmic approximation in log squared many rounds. And this is a result due to Esfandiari and others. And this result only holds if all the items have unit costs. So there's been quite a bit of work around this problem. And I just want to put things in context through a table. So when we look at independent items, then we had these 3 results that are relevant. So the first one is due to Agarwal and others. The second one is the Esfandiari and others. And the third row is the result that we get in this paper. So I'm comparing the approximation ratio in the second column and the number of rounds in the third column. So the paper of Agarwal and others has an approximation ratio that involves 3 logarithmic factors and a number of rounds which is logarithmic in their target Q. Esfandiari et al. Get an approximation ratio with 1 logarithmic factor, but more number of rounds, they need 2 logarithmic factors in the number of rounds. And our result gets a single logarithmic factor for both the approximation ratio and the rounds. And also we eliminate the unnecessary dependence on things like the maximum cost of an item and even the number of items. We have dependence only on the target value Q. In the correlated setting, this result of Grammel and others. So once again, the 3 columns are the same. The first column is the algorithm. The second one is the approximation ratio, and the third one is the number of adaptive rounds. So the earlier paper of Grammel and others gets a logarithmic approximation, but the number of rounds is unbounded, or it's equal to the number of items. If you combine it in a clever way with this recent paper of Esfandiari and others, you can get an approximation ratio that is logarithmic, but using a number of rounds that has two logarithmic factors. And our result, again, achieves the best of both these settings. It gets a logarithmic approximation ratio, which matches the fully adaptive bound. And it can achieve this in just a single logarithmic number of rounds. Okay, so for the next few minutes, I'll give some details on how we approach the problem with independent items. So the main idea here is to work with a partial cover problem, where our goal is not to cover the function entirely, but we just want to cover the function to an extent 1 minus delta. So think of delta as the fraction that we leave uncovered. So if you cover the function till it reaches a value of q, that's fully covering the function, but we now only want to cover the function till its value reaches 1 minus delta times q. So we are sort of leaving a delta fraction of the function uncovered. So we have a relaxed constraint over here. Instead of covering the function fully, we are covering it partially, but we want to find a non-adaptive list. So we want to come up with a list L, so which is a linear ordering on the items, which we are just going to probe along this fixed linear order until the value of the function exceeds our threshold, which is 1 minus delta q. So that's the non-adaptive partial cover. So that's what we will find as an algorithm. But we want to compare the cost of this non-adaptive algorithm to an adaptive algorithm that can sort of change its decisions after every instantiation. Right? So this picture on the right shows you an example of an adaptive solution that fully covers the function. So when you stop at any of these points, the function value must have reached the target q. But for the non-adaptive problem, when you stop, the function value only needs to reach 1 minus delta times q. So you have a weaker stopping criteria, but you need to find a non-adaptive solution. So the main result shows that we can indeed achieve such a goal, where the expected cost of the non-adaptive solution is only this factor, log of 1 over delta times 1 over delta. Right? So it depends on this gap parameter delta. So that's the blow up in the cost, but we are able to compare the cost to the optimal adaptive solution. And that's really the heart of the analysis, because structurally, it's not clear how you can relate otherwise the cost of a non-adaptive solution to an adaptive solution. So this really is our main technical result. So next, I want to outline how we can use this result to achieve the bounds for the R-round adaptivity gap. So this is a simple recursive idea, and I think I'll be able to explain it in this talk. So I'm going to give it a try at least. So we have an algorithm that takes as input these 4 parameters: the number of rounds R, the set of stochastic items X, a submodular function f, and the target function value q. Right? Q is always going to be the maximum function value. So if we reach a target of q, that means we've covered that submodular function f. So this is going to be a recursive algorithm. So what we do in the first step is to apply the non-adaptive partial cover algorithm that I just outlined in the previous slide. And we're going to use that with the parameter delta being q raised to minus 1 over r. So delta was the fraction of the function that was not covered. Right? So delta is a value between 0 and 1. So we set it to be this particular value. And what we do in round one is to probe the items in this list until we get a function coverage of 1 minus delta times q. So that's going to be our round one. And if P is the set of items that we ended up probing in round one, then we can formulate a residual submodular function that is conditioned on the outcomes in P. And you can formalize this by contracting the submodular function. But an important property is that if you contract any submodular function, you get another submodular function. So there is some closure property of submodular functions that we are using here. But I don't want to get into those details in the talk. Um, but yeah, you can look at the paper for more details. So if you take this residual submodular function that has already conditioned on the items that we probed in round one, then we'll also get a residual target, which is how much more we need to cover of this residual function so that we end up covering the full function. And so that sets up an instance that we can recurse on. And now we are going to recurse using one less rounds. So we have r minus one rounds, and we have fewer items because the items that we already probed, we cannot probe them again. So we remove those items from our list of original items. We have the residual submodular function and the residual target. So whatever we do recursively, those will be what we perform in the remaining r minus rounds, r minus one rounds, that is round number 2 up to round number r. Okay, so the result we can show about this recursive algorithm is that we get an r round algorithm where the expected cost is at most q to the 1 over r times log q times the adaptive value. So, and again, R is a tunable parameter. You can specify any value of R and you'll have a solution with that many rounds. Okay, so I'm going to attempt a proof of this result where we make use of the partial covering theorem and we prove the bound for the R round algorithm. So again, we have round one, which just follows what the non-adaptive partial covering algorithm does. And if we use that result directly, if you remember, there was this factor of 1 over delta times log 1 over delta. That was the approximation factor for the non-adaptive algorithm. And we are setting delta to be this value, q to the minus 1 over r. So if you plug that in, the expected cost in round one is going to be this quantity in red over here, q to the 1 over r times log q divided by r, the whole thing multiplied by the adaptive cost. So that's the cost incurred in round one. And when we go to round two, we are going to react or adapt to the observations P. So P is the set of items that we probed in round one, and we can observe their realizations. So conditioned on P, let's say that adaptive subscript P is the conditional optimal value of an adaptive solution that solves the residual submodular function, that covers the residual submodular function. So just by applying induction, we can say that the cost for the R minus one round algorithm, so we are just applying this inductively using R minus one rounds instead of R. And that's why we can use induction, right? It's smaller number of rounds. And the target value of the function is Q sub P. That's the target value of the residual function, not the original function. So if you just use this inductively, we get Q sub P raised to 1 over R minus 1 times log Q sub P. So that's the approximation that we get by induction. And then we use the fact that the residual function value, Q sub P, has to be less than delta times the original target Q, because in the first round, we covered 1 minus delta fraction of Q. So what is left is at most a delta fraction of Q. And if you plug in the value of delta, you can see that Q sub P is less than Q to the R minus 1 divided by R, right? So, and if you plug that in here and do some basic algebra, you get this expression on the right, 1 minus 1 over R times Q to the 1 over R times log Q, the whole thing multiplied by the adaptive value conditioned on P. So finally, when you take expectation over P, you will be deconditioning that. You can replace this adaptive subscript P by the original adaptive cost. And when you add what cost you suffered in round one with the cost in the remaining R minus 1 rounds, you get the sum of these two terms, the red and the green. And you can see that exactly this matches what you wanted to show. You have Q to the 1 over R times log Q times the adaptive value. Okay, so that might have been uh, a bit fast, but I mean, this is not a difficult proof. So that's, and I don't like to do a talk without any proof. So hopefully you got some sense of the analysis here. Okay, so one more thing about the partial cover algorithm. It's based on a very natural idea or a greedy type scheme where we build the list one item at a time, and each time we select an item that maximizes some score. So there's a kind of an interesting score. So I thought I'll explain the intuition behind this. So there are a few different terms in this. So we normalize the score by the cost of the item. So that's this term over here. And we take an expectation over all outcomes of the items that came earlier on this list. So those are these blue items over here, where we have an indicator or a filter which says that the non-adaptive policy does not stop after probing these items in the list. So it does not stop before getting to the item I. So that's what we have here. So this says that the stopping criteria is not achieved before reaching item I. And then we have the expectation over item I of the increase in function value. So we look at the function value using only the previous items in the list, that is x sub L, and then the function value after you add item I, right? So that's this union. And you look at the increase in the function value, and you also normalize it by the remaining distance to the target. So you can think of this red term over here as a relative increase in the function value when you add item I. So that's where the score comes from. And in each step, we add the item that maximizes the score, and that builds our non-adaptive list. Okay, so I'll skip this slide on the high-level analysis. I mean, and this is really the main part of the paper, but I mean, it's not possible to cover this in the talk. So I would refer you to the paper if you're curious. So that's all I wanted to mention about independent items. So moving on to the correlated case, I just have a one-slide summary pointing out the differences. So we now have a joint distribution over items. And as I mentioned, our performance bounds will depend on the support size of this joint distribution. And this support size will also be called the number of scenarios. That's standard terminology in stochastic optimization. So we have a similar high-level approach. We will again come up with a non-adaptive algorithm that is a partial cover. So it's not going to fully cover the function. But we need to change the criterion for a partial cover. So here, what we use is we either want to show that the number of compatible scenarios drops significantly. So in other words, originally you have all the S compatible scenarios. So everything in your support was a possibility. But after you perform one round, we want to say that the number of compatible scenarios drops to only a delta fraction. So only delta times S scenarios will be compatible. So either that happens or you end up fully covering the function. So one of these two must happen in every non-adaptive round. And once we define the partial cover algorithm or partial cover criteria in this manner, we can come up with another algorithm that finds a non-adaptive list L that has a similar expected cost, where we again compare to the expected cost of the adaptive solution. So this is really the main step where we use the power of adaptivity. We have a similar dependence here, like 1 over delta times log of q over delta. So it's a little worse than the independent case. If you remember the result for the partial cover in the independent case, it was 1 over delta times log of 1 over delta. So this one is a little worse. But once we have this main theorem, we can again use recursion, just like how we did for the independent setting, to get an R round algorithm that has expected cost S to the 1 over R times these logarithmic terms. And again, S is the support size of the distribution. And like I mentioned, there is no R round solution that can do much better, even if the function target is equal to 1. Right? So this dependence on S to the 1 over R is essential, not just for our algorithm, but for any algorithm. Okay, so I'll move on to the last part of the talk. So I already motivated our setting with these two applications, sensor placement, which was the stochastic set cover problem, and medical diagnosis, which is also called optimal decision tree. In the paper, we discuss a few other applications that can be captured in our framework. Next, I want to discuss some computational results that we uh, saw on these two applications. So the sensor deployment and medical diagnosis. So I'll first talk about the sensor placement application or the stochastic set cover problem. So we picked set cover instances based on two real world networks. So these are called the opinions and the Facebook messages data sets that were used in some previous papers. So in the opinions network, we have about 1,000 nodes and 57,000 edges. So it's a fairly dense network. And in the Facebook network, we have about 1,200 nodes and 6,400 edges. So the Facebook network is a sparse network. So we view these networks as instances of set cover in the following way. Every node corresponds to an item, and we assume that each node is going to cover each of its neighbors with probability 0.1. So that gives us a stochastic subset for every item. So if you pick a node, it's going to cover itself and each of its neighbors with a probability of 0.1. But you don't know before selecting any node which is the exact set of nodes that it'll end up covering. Right? So that's the stochastic aspect. And we set the target to be 50% of the nodes in the opinions network because it's a dense network. And for the Facebook network, we set the target to cover 25% of the nodes. So what that means is we want to select these items or nodes and observe the other nodes that they cover. And we want to continue the process until we cover the target number of nodes. If you're talking about the opinions network, we have to cover 50% of all the nodes. For the Facebook network, we need to cover 25% of all the nodes. So that specifies the stochastic set cover instance. And also all the costs are units. So we just want to minimize the expected number of nodes before we achieve this coverage. So on the opinions network, this is how our results went. So the blue curve gives the expected cost of our algorithm, and we vary it with the number of rounds of adaptivity. So With one round of adaptivity, which would be a non-adaptive algorithm, our cost is 57 point something. And by the time we come down to 7 rounds of adaptivity, our cost reduces to around 53. The orange line gives you the expected cost of our fully adaptive algorithm. And just to see how well our algorithms perform against the optimal value, which is very difficult to compute, we also came up with an information theoretic lower bound that's based on sampling. So what we do is we sample realizations of all the items, and that generates a set cover integer program that we can solve. For every realization, we solve a set cover integer program, and finally we average the optimal values from the set cover program. So you can also think of this as just a sample average approximation. So using a sample average approximation, we get an information theoretic lower bound, and we found that that value was around 40. So we are not very far off from the information lower bound on this instance. So there is some weird behavior here that when we increase the number of rounds, the objective value actually goes up, and that comes down to the fact that we are only estimating our objective value. So this is a very complicated problem to calculate the objective exactly. So what we do is we sample some number of decision paths and take the average, and that's what we are reporting as our objective. So and there could be some chance that the sampling missed out high cost or low cost events. So that's what would explain this kind of increase in expected value when you increase the number of rounds. So on the Facebook network, we see a similar behavior. By the time the number of rounds goes to 7, we have a cost that is very comparable to the fully adaptive algorithm that uses a very large number of rounds. And again, these costs are not very far from the information theoretic lower bound. So we also tested on instances of optimal decision tree. So here we used a data set from toxic response situation. So this is called the Wiser data set. So this has a number of toxic chemicals that people could be exposed to and symptoms that people would show when they are exposed to those chemicals. So there are about 415 chemicals and 79 symptoms that a first responder would need to check for. So what we want to do is, if we have some person who has been exposed to one of these 415 chemicals, we want to test for these symptoms and quickly identify what is the chemical that the person has been exposed to. So this is exactly the medical diagnosis situation. And again, we just model costs as units. So we want to minimize the number of symptoms checked before we identify the chemical. So this plot again shows the expected cost of our algorithm in blue as we increase the number of adaptive rounds. The orange line gives us the cost of the fully adaptive solution, and the red line gives us an information theoretic lower bound. And this time, there's a very simple lower bound that we can use, which is just the entropy. So the entropy is the log base 2 of the number of scenarios, or the number of chemicals. And we can see that very quickly, in about 3 rounds, our 3 round adaptive algorithm does almost as well as the information theoretic lower bound. So in this case, our algorithm performs very well. Okay, so I'll just conclude in this final slide. So we looked at the impact of rounds of adaptivity in the stochastic submodular cover problem, and we could achieve a smooth trade-off between approximation and the number of rounds, both when you have independent items and correlated items. So the algorithms we got are easy to implement, and we did implement them and found that the empirical performance was good. There are a few open problems remaining. It's still interesting to pin down the exact adaptivity gap for set cover. So combined with our result and the previous paper of Gomans and Wondrak, we know that the adaptivity gap has to lie between D and D times log D, where D is the number of objects in set cover. It would be very interesting to pin it down. And more broadly, it's an interesting goal to quantify the role of adaptivity in other stochastic settings. So there are some recent papers that look at the role of adaptivity in, for example, the stochastic multi-armed bandits problem. But there are a number of other stochastic optimization problems where we can try and identify this kind of a quantitative trade-off between number of rounds and the performance guarantee. Okay, so I'll end with that. Thank you.